Hello everyone, my name is Naina and I'm from the Pudi Academy. So today we'll continue with the chapter that is chemical bonding and molecular structure. So in today's video we will see basically the ionic or the electrovalent bond, lattice enthalpy and some of the bond parameters. So let's start. So first one is the ionic or electrovalent bond. The ionic bond basically it is formed between two ions. Now those ions can be either a positive or a negative ion. So from Kossel and Lewis treatment of the formation of ionic bond, it follows that the formation of ionic compounds would primarily depend upon. Now what are the factors on which the formation of ionic bond depends upon? Now the ease of formation of positive and negative ions from the respective neutral atoms. So if you have a neutral atom, for example NaCl is a neutral atom. Now the ease with which it can form a positive and a negative ion. For example, if we split NaCl, it will form Na plus and Cl minus. So this is for sure. When if we split NaCl, we can get a sodium and a chlorine ion, which is positive and negative respectively. So the ease at which the formation of positive and negative ion of the neutral atom. Now the arrangement of the positive and negative ions in the solid, that is the lattice of crystal compound. Now once there is a positive and a negative ions, they should be arranged in a solid form. For example, this salt, so it forms a lattice of crystalline compound, something like this. This is the salt structure. Now the formation of a positive ion involves ionization. So whenever there is a formation of positive ion, it involves ionization. Ionization means there is removal of one electron. So when from a neutral atom, when we remove one electron, it forms the positive ion. So it requires ionization enthalpy because there is removal of electron that is involved from the neutral atom. Negative ion involves addition of electron. Now negative ions are formed when a neutral atom takes up an electron. That time we get a negative atom. It involves electron gain enthalpy. So energy required to take up one electron. So the overall reaction will be positive plus negative, it will give you a neutral molecule. Now the electron gain enthalpy, that is delta EGH, is the enthalpy change when a gas phase atom in its ground state gains an electron. So when a molecule is in its gas phase, and in ground state when it gains an electron, that is what electron gain enthalpy is, and it is denoted by delta EGH. Delta H stands for ionization enthalpy. EGH stands for gain enthalpy, electron gain enthalpy. Now the electron gain process may be exothermic or endothermic. So the electron gain process, it can be exothermic or endothermic. The ionization on the other hand is always endothermic. So electron gain process, it can be either exothermic or endothermic, whereas ionization is always endothermic in nature. Now, electron affinity is the negative of the energy change accompanying electron gain. So obviously ionic bonds will be formed more easily between elements with comparatively low ionization enthalpies and elements with comparatively high negative value of electron gain enthalpy. So the ionic bond, it will basically form between two atoms, one with relatively low ionization enthalpy and one with relatively high electron gain enthalpy, because if the electron gain enthalpy is more, then only the molecule will pull the electron towards itself. For example, NaCl. Cl being highly electronegative, it will pull the electrons from sodium, which will create the positive and negative signs on both of them. Hence there is a formation of ionic bond. So To form an ionic bond, one should have a relatively low ionization enthalpy and one should have a relatively high electron gain enthalpy. Most ionic compounds have cations derived from metallic elements and anions from non-metallic elements. So, most of the ionic compounds that are formed, they have a metallic cation and non-metallic anion. Now, for example, ammonium, made up of two non-metallic elements, is an exception. So, every situation there is an exception. Here the exception is ammonia. Okay. It forms the cation of a number of ionic compounds. Now, ionic compounds in the crystalline state consist of orderly three-dimensional arrangement of cations and anions held together by a Coulombic interaction energies. So, whenever there is an ionic compound, there is a crystalline structure which is formed, okay, which is a 3D structure of cation and anion which are held together by some Coulombic interactions or energies. These compounds crystallize in different crystal size structures determined by size of the ions. So depending on their size, okay, of the ions, the compound crystallizes in different crystal structures. Now this is the structure of a rock salt, okay, but other ionic crystals will have a structure different to this. It is based upon their sizes. Some will have bigger size, some will have smaller size, some will have same sizes. So depending upon the sizes of the atoms, the structures will differ. Now the packaging arrangement and other factors also are determined by the sizes, okay, how they are packed, how they are arranged. Other factors also determined by the size of the ions. Now, in ionic solids, the sum of electron gain enthalpy and the ionization enthalpy may be positive, but still crystal structure gets stabilized due to energy released in the formation of crystal lattice. So, in an ionic solid, the sum of electron gain enthalpy and ionization enthalpy, when you add both the enthalpies, both the energies required to take up an electron, required to remove an electron, okay, even though this total will give you a positive value, but still the crystal structure gets stabilized due to the energy which is released by the formation of crystal lattice. So whenever there is a formation of crystal lattice, that time energy is released, and because of that energy release, the structure is stabilized. For example, ionization enthalpy for sodium Na plus formation, okay, sodium positive ion formation from sodium, okay, while the electron gain enthalpy of the chlorine, okay, one is 495.8 kilojoules is your ionization enthalpy, whereas negative 348.7 kilojoules is your electron gain enthalpy. The sum of both, you will get 147.1 kilojoules per mole, is more than compensated for the enthalpy of lattice formation. Now therefore the energy released in the process is more than the energy absorbed, okay. Now thus a qualitative measure of the stability of an ionic compound is provided by its enthalpy of lattice formation and not simply by achieving octet of electrons around the ionic species in a gaseous state. Now here you can see the total energy that is absorbed is 147.1 kilojoules per mole, but the energy that is required to form a lattice is negative 788 kilojoules per mole, okay. So here you can conclude that the energy, okay, the energy released in the process, okay, is more than the energy which is absorbed during the process. So thus you can say that the stability of ionic compound, okay, it is provided by its enthalpy of lattice formation. So the energy which is required to form the lattice, that energy provides the stability to the ionic compound, and it is not simply because of the octet of electrons around the ionic species. So since lattice enthalpy plays a key role in the formation of ionic compounds, it is important. Okay, since everywhere in this concept we have learned that there is lattice enthalpy which plays an important role. So it is important for you all to know what is lattice enthalpy. Okay, so next concept is your lattice enthalpy. Now the lattice enthalpy of an ionic solid is defined as the energy required to completely separate 1 mole of solid ionic compound into gaseous constituent ions. So what is lattice enthalpy? It is the energy required to completely separate, okay, 1 mole of solid ionic compound into gaseous constituent ions. So if you have NaCl, okay, so the energy which is required to separate 1 mole of this NaCl into its gaseous constituent, that are sodium and chlorine ions. Okay, so this is what lattice enthalpy is. For example, lattice enthalpy of NaCl is 788 kilojoules per mole. Now this means that 788 kilojoules of energy is required to separate 1 mole of solid NaCl into 1 mole of sodium gas and 1 mole of chlorine gas to an infinite distance. Got it? As I told you, so it is the energy required to separate this NaCl molecule into its 2 consequent gas components. Okay, so here the energy is 788 kilojoules. So 788 kilojoules is required to separate 1 mole of NaCl into 1 mole of sodium gas and 1 mole of chlorine gas. This process involves both the attractive forces between ions of opposite charges and the repulsive forces between ions of the like charges. Now, in this process, which of the forces are involved? In this process, 2 forces are involved. One is the attractive forces between Na plus and Cl minus, and repulsive forces between Na plus and Cl minus. For example, here in this structure I can show you. So there is an attractive force between these 2 components. For example, this is sodium and this is chlorine. So there is an attractive force between these 2 molecules and there is a repulsive force between these 2 molecules. Okay. Now the solid crystals being 3-dimensional, it is not possible to calculate lattice enthalpy directly from the interaction of forces of attraction and repulsion only. Factors associated with the crystal geometry have to be included. Now since it is a 3-dimensional structure, you cannot directly calculate the lattice enthalpy only by using the attractive and repulsive forces. Here you have to also take note of the crystal geometry that have been included. Okay, now what is their geometry, what is the distance, what are the structure, how they are packed. Okay, these are all the concepts of crystal geometry. This is there for you in 12th standard in solid state chapter. Next is the bond parameters. So bond parameters involve, first one is your bond length, the length of the bond. Now bond length is defined as equilibrium distance between the nuclei of 2 bonded atoms in a molecule. Now if you have 2 atoms which are bonded together, okay, bond length is the distance between the nuclei of both the atoms. So nuclei of this atom and nuclei of this atom, this distance. For example, if you take 2 circles, each center, okay, when you connect them center to center, this distance is known as your bond length. Okay, now bond lengths are measured by spectroscopic X-ray diffraction and electron diffraction techniques, about which you will learn in higher classes. Now how you will determine the bond length? Now bond length can be determined using spectroscopic method, X-ray diffraction and electron diffraction techniques. About these techniques you will learn in your higher classes. Now each atom of the bonded pair contributes to the bond length. Okay, it's not like bond length is involved with one atom, but both of the atom equally contributes to the bond length. In case of covalent bond, the contribution from each atom is called the covalent radius of the atom. Okay, now since both the atoms they are bonded together, they contribute to the bond length. In case of covalent bond, we call it covalent radius of the atom. Now, the covalent radius is measured approximately as the radius of an atom's core, which is in contact with the core of an adjacent atom in a bonded situation. So when you have a bonded pair, okay. So covalent radius we measure it is a measure of approximately the radius of an atom. So this is the radius of an atom's core, which is in contact with the core of the second atom. Okay, now you have atom 1 and atom 2. Both the cores, when they are connected together, this is what covalent radius is. Now the covalent radius is half of the distance between two similar atoms joined by covalent bond. It is the half the distance between the two similar atoms which are joined by a covalent bond in the same molecule. Now the van der Waals radius represents the overall size of the atom, which includes its valence shell in a non-bonded situation. Now there are van der Waals radius, which represents the overall size. For covalent, it is just the core to core distance. It is not like entire distance we are measuring. We are just measuring the radius of both the atoms. Now van der Waals radius represents the overall size. Overall size means from end to end. Overall size of the atom, which includes its valence shell in a non-bonded situation. Now this also includes its valence shell also. Now further, the van der Waals radius is half of the distance between two similar atoms in separate molecules in a solid. So further, if you want to take, you have to take the half distance between two similar atoms. Now covalent and van der Waals radii of chlorine are depicted here. Now this is the covalent and van der Waals radius of chlorine atom. Here you can see half the distance and your complete distance. Now some typical average bond lengths for single, double and triple bonds shown in table 4.2. Here there is the bond length of some simple single, double and triple bond molecules. What are their bond lengths? Next is the bond angle. Now it is defined as the angle between the orbitals containing bonding electron pairs around the central atom in a molecule or a complex ion. Now what is bond angle? It is the angle between the bonding electron pairs around the central metal atom or complex ions. Now here water is the example that they have taken. Here oxygen is the central atom and it is connected to two hydrogens, and you have two lone pairs or unbonded electrons. Because of this unbonded electrons, there is repulsion, due to which instead of a linear structure you have a bent structure, and this bent structure has a angle of 104.5 degree. Okay, now bond angle is expressed in degree, which can be experimentally determined by spectroscopic methods. Now, it gives some idea regarding the distribution of orbitals around the central atom in a molecule, complex ion, and hence it helps us determining its shape. So basically bond angle will help us determine its shape, as it will tell you the distribution of orbitals around the central atom in a molecule or in a complex ions. Now for example, water molecule, it should have a linear structure like this, but because of this unpaired electrons there is a repulsion that is faced, and due to that we have a bent structure with an angle of 104.5 degree. Now next is bond enthalpy. Now, you have seen about ionization enthalpy and electron gain enthalpy. Now, something similar is your bond enthalpy. Now it is defined as the amount of energy that is required to break 1 mole of bond of a particular type between two atoms in a gaseous state. Okay, so in short you can say bond enthalpy, it is the amount of energy that is required to break a bond. Okay, now the unit of bond enthalpy is kilojoules per mole. Unit of enthalpy is kilojoules per mole. So bond enthalpy will also have same unit. Now for example, we have hydrogen bond. Okay, hydrogen bond require 435.8 kilojoules per mole to break this H2 molecule, that is hydrogen molecule, into two hydrogen gases. Okay, so in simple words, bond enthalpy, it is the energy that is required to break a bond. Now it is important that the larger the bond dissociation enthalpy, stronger will be the bond in the molecule. So in short, as you increase the enthalpy, okay, as you increase the enthalpy means you are increasing the energy, that means the bond is stronger. So the more the energy required to break a bond, more stronger is the bond in the molecule. Okay, now in case of polyatomic molecules, the measurement of bond strength is more complicated. Now it is simple for molecules like H2, N2, O2, HCl, NaCl, because there is only single bonds that are involved. So you can easily determine their bond enthalpy. Whereas when you have a polyatomic molecules, okay, when there are more than two bonds which are involved, it makes complicated to measure the enthalpy, because both the bond will have two different types of energy requirements to break. For example, if I take water molecule, okay, the enthalpy needed to break two OH bonds. Now here water molecule, it has two similar bonds, both are OH, yes or no, both are OH bonds, but when you measure their bond enthalpy, the thing that is observed is to break one of this OH bond, it requires 502 kilojoules per mole of energy to break one of the OH bond. If I break one of the OH bond, what will remain is the another OH bond. Now to break this single OH bond, it requires 427 kilojoules per mole. Now the difference, since both are OH bonds, but the energy required to break both the bonds differ. Now this is basically because the second OH bond, okay, first one is broken. Now the second OH bond, it undergoes some changes because of the changed chemical environment. Now water molecule has two OH bonds, right? Once this OH bond is broken, what happens? The oxygen will have the electrons which were initially associated with this hydrogen will now again come back to oxygen. Now here what happens? The chemical environment of this OH is changing, right? Now because of this change in chemical environment, the second bond enthalpy changes. Now this is the reason for some differences in energy of the OH bond in different molecules. Now similarly you can see for ethanol. Okay, to break some bonds, once you break the bonds, the other bonds will face some chemical changes, and that chemical changes will lead to their increase or decrease in the second bond enthalpy. Now, therefore, in polyatomic molecules, the term mean or average bond enthalpy is used. You cannot say that this is the bond enthalpy of that molecule, because each bond has different bond enthalpy. So you have to take a mean or average bond enthalpy for polyatomic molecules. Now it is obtained by dividing the total dissociation enthalpy by the number of bonds broken. Okay, now how you will find the mean or average bond enthalpy? The mean or average bond enthalpy is found by adding both the enthalpies. Now for example, for water molecule, two OH bonds are broken. The first OH bond has an enthalpy of 502, second OH molecule has an enthalpy of 427. Now you have to add both the enthalpies and divide it by the number of bonds that are broken. Now here we have broken 2 bonds, so divided by 2. Whatever answer you get, that is the average bond enthalpy for water molecule. Okay, this is how you will find bond enthalpy. Next is a bond order. Now, in the Lewis description of covalent bond, the bond order is given by the number of bonds between two atoms in a molecule. Now, what is bond order? It is the number of bonds between two atoms in a molecule. Okay, bond order is basically the factor that tells you about the number of bonds that are formed between the molecules. Now, for example, H2 with a single shared electron pair. Now, in O2 we have 2 shared electron pairs, and in N2 we have 3 shared electron pairs. That means hydrogen we have 1 electrons that are shared, so a single pair. For example, for oxygen we have total 4 electrons that are involved, forming a double bond. For nitrogen, total 6 electrons are involved, forming a triple bond. Okay, so there is, for H2 you have a single shared electron pair, for O2 you have a 2 shared electron pairs, and for N2 you have 3 shared electron pairs. In short, you have 1, 2 and 3 respectively. So the bond order will be, for hydrogen it will be 1, for oxygen it will be 2, and for nitrogen it will be 3. Now similarly in CO, okay, carbon monoxide, there is 3 shared electron pairs between carbon and oxygen. So between carbon and oxygen there are 3 shared electron pairs similar to nitrogen. So the bond order is 3. Okay, so the number of bonds that are formed is basically what your bond order is. Now, isoelectronic molecules and ions have identical bond orders. For example, F2 and O2 2- have bond order of 1. Now, isoelectronic molecules and ions. Isoelectronic molecules and ions means the molecules with same electrons. Okay, for example, we say hydrogen and hydrogen-like molecules, right? Hydrogen with 1 electron. When you helium has 2 electrons, but when you remove 1 electron, helium becomes He1, which is similar to hydrogen. So something like this, isoelectronic molecules means the molecules with same electronic configuration or same electrons in them. Those molecules will have an identical bond order. Here they have given an example of F2, that is fluorine 2. Fluorine 2 and oxygen 2-. Here 2 electrons of oxygen is added. Now in this case the bond order is 1. Second example is nitrogen, carbon monoxide and nitrogen monoxide have a bond order of 3. All these 3 molecules have triple bonds in them. Okay. Now, a general correlation useful for understanding the stability of molecules is that with increase in bond order, bond enthalpy increases and bond length decreases. So this point is very important. This is a general relationship or understanding between the 3 concepts that we have learned so far. That is bond order, bond enthalpy and bond length. Now, as you increase the bond order, that means as you increase the number of bonds, the bond enthalpy will also increase, because as you increase the number of bonds means you are increasing the bonds that are to be broken. Okay, so the energy will be more, right? So bond enthalpy will also increase and bond length will decrease. So what is the relation between all 3? As you increase bond order, bond enthalpy will increase and bond length will decrease. So this is very important. Next is the resonance structure. Now, it is often observed that a single Lewis structure is inadequate for the representation of a molecule in conformity with its experimentally determined parameters. So when you observe a single Lewis structure, okay, for the representation of a molecule, in conformity with its experimental determined parameters, for example the ozone molecule. Okay, the ozone is O3, can be equally represented by the structure 1 and 2 shown below. Now this is the structure of ozone. Okay, it can be represented in both the ways. Okay, you can show double bond on the left hand side also and on the right hand side also. Okay, now in both the structures we have OO single bond and OO double bond. Right, now the normal single and double bond of oxygens are 148 picometers and 121 picometers respectively. So these are the bond lengths. For single bond it is 148 picometers and for double bond it is 121 picometers. These are the bond lengths. Now, experimentally determined oxygen-oxygen bond length in O3 molecule are same. Now, thus the oxygen-oxygen bonds in O3 molecule are intermediate between a double and a single bond. Now, since both the bonds they are intermediate means you can have a structure like this also, or you can have a structure like this also. Both the structures can exist in the environment. Now obviously this cannot be represented by either of the two lattice structures shown above. Now the concept of resonance was introduced to deal with the type of difficulty experienced in the depiction of accurate structure of molecules like O3. Since O3 has two structures, either it can have structure 1 or it can have structure 2. Now, since it can be present in either of the structure, there is a difficulty to represent which structure is actual, whether this one or this one. So to remove this difficulty, the concept of resonance was introduced. Okay, for molecules like O3. There are other molecules also which follow the similar pattern. A basic example is benzene. Okay, basic example is benzene. In benzene, all these three double bonds can resonate. Resonate means they can move around. Now, for example, this bond will go here, this bond will come here, this bond will go here. So it will be like this. So you can get various resonance structures. Now, which one is the original structure, or which one is the actual structure in which benzene exists, or for that matter ozone exists? That we can't predict, right? So to remove such difficulties, the concept of resonance was introduced. Now, according to the concept of resonance, whenever a single lattice structure cannot describe a molecule accurately, a number of structures with similar energy, position of nuclei, bonding and non-bonding pairs of electrons are taken as the canonical structure of the hybrid which describes the molecule accurately. So according to this concept, okay, whenever you have a single lattice structure which you cannot describe in, or which you cannot describe accurately which structure it has, in that situation you can give a hybrid structure with a number, hybrid structure with various number means you can put n number of structures, okay, with similar energy, position of the nuclei is also similar, bonding and non-bonding pairs of electrons are also same, but the structure will be canonical. Canonical means there will be like this, either the double bond will be on left hand side or it will be on a right hand side. Okay, you can show them in a canonical form. Thus, for O3, the two structures shown above constitutes the canonical structure or resonance structure, and their hybrid is structure 3. So, in short, what you can do is, these are resonance structure or canonical structures, and together you can show this hybrid structure. Now, this dotted double bonds on both the side means this double bond can either be present on right hand side or on the left hand side. Okay. Now this is called resonance hybrid. Okay, so the third structure is called as resonance hybrid. So this is your resonance hybrid structure for ozone. Now resonance is represented as by a double-headed arrow. So resonance structure, basically between two structures we show a double-headed arrow. For reactions we show single-headed, or we show something like this. This means it is a reversible reaction. This means it is a one-way reaction, and this arrow depicts the resonance structure. Now, some of the other examples of resonance structures are carbonate ions and carbon dioxide molecules. Here they have given you the resonance structure of carbonate, that is CO3, and carbon dioxide molecule. Now, in general, it may be stated that resonance stabilizes the molecule as the energy of the resonance hybrid is less than the energy of any single canonical structure. So in short, what resonance does is it stabilizes the molecule, because the single canonical structure, the energy of single canonical structure compared to the resonance hybrid structure, okay, as the energy of the resonance hybrid structure is less compared to the energy of the single canonical structure. Now, second, resonance averages the bond characteristics as a whole. So here you can also see that we have two bond lengths, but in a hybrid structure we have an average bond length, that is 128 picometers. So resonance, it averages the bond characteristics as a whole. Now, thus the energy of the O3 resonance hybrid is lower than either of the two canonical forms. So this structure has a lower energy than either of these two canonical structures. Next is the polarity of the bonds. Okay, this is the last parameter, that is the polarity of a bond. Now the existence of 100% ionic or covalent bond represents an ideal situation. Okay, in reality, no bond or compound is either completely covalent or ionic. We say that a bond is covalent or ionic, but in reality, none of these bonds are completely covalent or completely ionic. Even in cases of covalent bond between two hydrogen atoms, there is some ionic character. Okay, so when covalent bond is formed between two similar atoms, for example hydrogen, nitrogen, chlorine, okay, that is H2N2O2, the shared pairs of electron is equally attracted by the two atoms. Here also you can see, since both the atoms are similar, okay, we tend to say there is no ionic bond formation, it is basically the covalent bond formation, right? But there is also an attraction force that is between these atoms. So as a result, electron pair is situated exactly between the two identical nuclei. Okay. Now the bond so formed is called non-polar covalent bond. Okay. Since both the electron pairs, they are situated between the two identical covalent bonds. Okay. Here there is no ions that are involved, it is just an attraction that is involved. This type of bonds are called as non-polar covalent bond. Contrary to this, in case of heteronuclear molecule, now non-polar covalent bonds, basic example is your homonuclear, that are H2, N2, O2, okay, means both the atoms are similar. For example, in case of heteronuclear molecule, heteronuclear means two different atoms, for example HF. Okay, the shared electron pairs between the two atoms get displaced more towards fluorine, since the electronegativity of fluorine is far greater than hydrogen. Now, when there is a bond formation between hydrogen and fluorine, okay, fluorine being highly electronegative, the electron that is associated with the bond formation is more towards the fluorine. Okay, if you want to show the concept in a cloud form, okay, then the cloud near hydrogen will be smaller, whereas the one around fluorine will be greater, because fluorine being highly electronegative, it pulls the electron towards itself, both the electrons towards itself. Okay, now the resultant covalent bond is polar covalent bond. Okay, so here the bond which is formed is a polar covalent bond. Polar means towards one molecule there is more power. Okay, as a result of polarization, the molecule possesses a dipole movement depicted below, which can be defined as the product of the magnitude of charge and the distance between the centers of positive and negative charges. Now, what is dipole moment? It is defined as the product of magnitude. Magnitude means the product of the charge, okay, towards whom the charge is more, okay, between the centers of the positive and negative charges. Now here hydrogen will be a positive and fluorine will be a negative charge, right? So there is a bond formation between them. So here there will be a value of charge because the electrons are more towards, or the pull is more towards fluorine. Now it is usually designated by a Greek letter mu. Now how you will calculate the dipole movement? Usually it is represented by mu. Okay, so dipole movement is equal to charge into distance of separation. So it is basically the charge into the distance of separation. Dipole moment is usually expressed in dBA units. Okay, the unit of dipole moment is dBA, that is D. Now the conversion factor is, now how you will convert it? So 1 dBA, 1 D is equal to 3.33564 into 10 raised to minus 30 coulombs per meter. Coulombs meter. C stands for coulomb, M stands for meter. Now why it is coulomb meter? Charge, the unit of charge is coulomb, and the distance, it is in meter, so it is in coulomb meter. Now further, dipole moment is a vector quantity, and by convention it is depicted by a small arrow with a tail and on the negative center and head pointing towards the positive center. It is a vector quantity. It has a magnitude and it also tells you the direction. Okay, now how you will know the direction? It is depicted in a small arrow. Okay, now the tail on the negative center and head pointing towards the positive center. Okay, now but in chemistry, presence of dipole moment is represented by a cross arrow. Okay, normally it is the tail with negative and head with positive, but in chemistry we will represent a dipole moment in a crossed arrow put on Lewis structure of the molecule. Now the cross is on positive and arrowhead is on negative end. So this is how we represent a dipole movement, with an arrow with a cross. Now this cross part is for positive end and this head part is for negative end, or this cross is towards the positive and head is towards the negative. Now here you can see for HF, okay, since fluorine has more electrons and the electron is pulled towards fluorine, okay, the head will be towards fluorine and the cross will be towards hydrogen. Now this arrow symbolizes the direction of the shift of electron density in the molecule. Now what this arrow symbolizes? It symbolizes the shift of electrons, where the electrons are more, or towards which atom is the electron density more, or more electrons are present. So here towards fluorine the electrons are more. Note that the direction of crossed arrow is opposite to the conventional direction of dipole vector. Now, in case of polyatomic molecule, the dipole moment not only depend upon the individual dipole moments of the bonds known as bond dipoles, but also on the spatial arrangement of various bonds in molecule. Now, in polyatomic molecule, it not only depends upon the individual dipole moment but overall dipole moments. Okay, for example, in water molecule we have two OH bonds. Okay, now the dipole moment will not depend on any one of the hydrogen or OH bond. It will depend on the both of the OH bonds. Now here both the dipole moments are towards oxygen, right? So the dipole moment in general will be, or the resultant dipole moment will be like this, because both are towards oxygen. So this will be the resultant dipole movement. Now, in such cases, the dipole moment of a molecule is a vector sum. Vector sum means the dipole moment of various bonds added together. Okay. Now, for example, water molecule, which has a band structure. The two OH bonds are oriented in an angle of 104.5 degree. Right. Now, net dipole moment will be 6.7 into 10 raised to 30 coulombs per meter. Now, in the resultant dipole moment of two OH bonds, here both the OH bonds are considered and the resultant dipole moment is taken. Now, the dipole moment in case of BeF2 is 0. Beryllium difluoride. In case of BeF2, the dipole moment is 0 because the dipole moments are on opposite directions, so they cancel out each other. Okay. So this is because the two equal bond dipole points in opposite direction and cancels effect of each other, since they are on opposite direction with equal force. So they cancels out each other. Now in tetraatomic molecules, for example in BF3, the dipole moment is 0. Although the BF bonds are oriented at an angle of 120 to one another, the three bond moments give a net sum of 0 as a resultant of any two is equal and opposite to the third one. Now in tetrahedral structures also same thing happens. The overall polarity is 0 because here all the three bonds are arranged in an angle of 120 degree. Okay. Now there are three bond moments which are there. One is towards your left hand side, and there are two. Okay. Now the resultant of both this will be in the opposite direction. Okay. So the net sum is 0 because the resultant of any two is equal and opposite to the third one. Now any two of them, you can take any two, either these two, any two of them are equal and opposite to the third one. So it cancels out. Let us study an interesting case of NH3 and NF3 molecules. Both the molecules have a pyramidal shape with a lone pair of electron on nitrogen atom. Although fluorine is more electronegative than nitrogen, the resultant dipole movement of NH3 is greater than that of NF3. This is an important question. Okay, why the resultant dipole moment of ammonia, that is NH3, is greater than that of NF3? You have to explain this. There are many papers in which this question has come. The resultant dipole moment of NH3 and NF3, one is greater than the other. Both have similar structure. Okay, with each having a single lone pair. Here you can see both, and this is NH3 molecule and this is NF3 molecule. Okay, both are having similar structure but their dipole moments differ. Now why NH3 has a greater dipole moment than NF3? This is because in case of NH3, the orbital dipole due to lone pair is in the same direction as the resultant dipole moment of NH bonds. Okay, now for NH3 what happens? The dipole moment of the lone pair is in the direction towards the lone pairs. Now the other dipole moments of hydrogen NH bonds, okay, the dipole moment of NH bonds and the dipole moment of lone pair, all of them are in one direction. In one direction means all of them are pointing towards the lone pair, or all of them are pointing towards the upward direction. So the orbital dipole due to lone pair is in the same direction as the resultant dipole of the NH bond. So the dipole moment of lone pair is in the same direction of the resultant dipole moment of the NH bond. Okay, whereas in NF3 the dipole moment is in the opposite direction to the resultant dipole moment of 3 NF bonds. Now in case of NF3, what happens? The lone pair, okay, the dipole moment of lone pair is towards the up, okay, towards the lone pair, whereas the resultant dipole moment of the NF bond is downwards. Okay, now here all the bonds are going upwards. Here one is upwards, one is downwards. So the resultant dipole moment for NF3 will decrease because they are in opposite direction. So there will be some kind of cancellations or opposing forces which are there. So the resultant dipole moment for NF3 will be less than the resultant dipole moment of NH3. Okay, because in NH3 all the dipole moments are towards one direction, whereas in NF3 the dipole moment of lone pair is towards the towards up, and whereas the resultant dipole moment of NF bonds are straight opposite to the dipole moment of lone pairs. Hence the dipole moment of NH3 is greater than the dipole moment of NF3. Now the orbital dipole, because of lone pair, decreases the effect of the resultant NF bond movements, which results in low dipole movement and of NF3 as represented below. So both of them are in opposite direction, there is some kind of repulsive energy which is taking place, and due to this the lone pair, it decreases the effect of resultant NF bond movements. Just as all the covalent bonds have some partial ionic character, the ionic bonds have a partial covalent character. Okay, all the covalent bonds, they have a partial ionic character, because even though both the atoms which are involved, they have a ionic character towards themselves, so they have a partial ionic and a partial covalent character. Now, the partial covalent character of ionic bonds was discussed by Fazan in terms of the following rules. Now on what point did the partial covalent character of an ionic bond was discussed? It was discussed by Fazan's. Now it is discussed in terms of the following rules. First one is the smaller size of the cation and the larger size of the anion, the greater the covalent character of an ionic bond. Now when you have a smaller size cation, okay, if the size of cation is smaller and the size of anion is larger, the covalent character of an ionic bond is greater. Now the greater the charge on cation, the greater the covalent character of ionic bond. If the charge on cation is high, okay, it's greater. If you have +2, +3, you have a greater ionic charge, then the covalent character of ionic bond is higher. Now for cations of the same size and charge, the one with similar electronic configuration, typical of transition metals, is more polarizing than the one with a noble gas configuration, typical of alkali and alkaline earth metal cations. Now for cations, okay, with same size and charge, okay, for example your transition metals being close together, like they have one electron ka difference in them, right? So they have same size and charge, the size difference will not be much. For those elements, they are more polarizing than the ones with a noble gas configuration. Okay, noble gas configuration, they have a relatively stable structure and they are inert in nature. So compared to noble gas, the transition metals with same size and charge have a more polarizing nature. Now the cations polarizes the anions, pulling the electronic charge towards itself and thereby increasing the electronic charge between the two. Now who polarizes whom? Cations, they polarizes the anions by pulling the electronic charge towards itself and thereby increasing the electron charge between the two. Now this is precisely what happens in a covalent bond. Okay, that is buildup of electron charge density between the nuclei. So in a covalent bond, what happens? There is a nuclear or electron charge density which is built up between the nuclei. Now the polarizing power of cation and polarizability of an anion and the extent of distortion, that is polarization of anion, are the factors which determine the percent covalent character of an ionic bond. Now who determines the covalent character of the ionic bond? It is basically the polarizing power of an cation. How powerful is the cation to polarize it? And the polarizability of an anion. How powerful is the cation to polarize the anion, or how weak the anion is to get polarized, and the extent of polarization of an anion, okay, is what determines the covalent character of an ionic bond. So in today's video we have seen about the polarization of a bond. We have also seen resonance structures, bond enthalpy, that are bond parameters like bond length, bond order, bond angle, bond enthalpy, and we have also seen lattice enthalpy and what are ionic or electrovalent bond. So thank you for watching my video. Please do like, share and subscribe to our channel.